Hello and welcome. Today we're diving into a really fascinating breakthrough in the world of physics and engineering. We're talking about light, lasers, and how a new chip design is changing the game.
That's right. We are looking at research coming out of JQI, that's the Joint Quantum Institute. They've designed a new type of photonic chip that can take a single color of laser light and passively convert it into a whole range of other colors.
And just to set the stage here, manipulating light is a huge deal. It's a global market worth hundreds of billions of dollars. We use light for everything from the super accurate atomic clocks that keep our GPS working to moving massive amounts of data through fiber optics.
Exactly, but there's been a long-standing challenge. Engineers have wanted a compact light source, something that fits right on a chip, that can turn one laser color into a rainbow of other colors. This is crucial for things like quantum computers or making precise measurements of time.
So usually when I think of splitting light into a rainbow, I think of a prism. Is that what's happening here?
It's actually quite different. A prism just splits up colors that are already inside the beam. These new chips are doing something much harder. They are generating entirely new colors that weren't there to begin with.
Oh, I see. So it's not just separating, it's creating.
Precisely. This involves what physicists call nonlinear interactions. In a normal linear interaction, like a prism, light bends, but its frequency, which determines its color, stays the same. But if you concentrate light intensely enough, it can actually alter the behavior of the device it's passing through. That feedback loop creates new frequencies.
That sounds difficult to achieve. I imagine these non-linear signals are pretty faint.
They are. In fact, there's a funny story about that. Back in 1961, when researchers first observed this effect, the data point on the photo was so small that an editor thought it was a smudge and actually removed it from the published paper.
Wow, they deleted the discovery. That's incredible.
It really is. But today, we don't rely on accidents. Researchers use things called photonic resonators. Imagine tiny rings on a chip. The light goes in and circulates hundreds of thousands of times. Each trip around the ring boosts that nonlinear interaction, making the effect strong enough to use.
Okay, so we have these tiny rings trapping the light to change its color. What's the catch? Why hasn't this been solved before?
The catch is what they call frequency phase matching. It's a balancing act. To turn one color into another, say to double the frequency, the resonator has to support both the original color and the new color perfectly.
Like a guitar string that only hums at certain notes.
Exactly. But it's even trickier. The light waves for both colors have to travel at the same speed around the ring. If they get out of sync, the conversion fails. One of the lead authors, Lida Exuda, compared it to a solar eclipse. The sun and moon have to overlap perfectly. If you're off by a tiny bit, you see nothing.
And I assume manufacturing tiny chips to that level of perfection is hard?
Nearly impossible on a mass scale. Usually, tiny manufacturing errors ruin the alignment. To fix it, engineers have to install little heaters on the chips to actively tune the materials. It consumes power and complicates the design.
But this new JQI research claims to solve that, right? Without the heaters?
Yes. And the solution was almost a surprise. The team, including lead author Mahmoud Jalali Mehrabad, used an array of resonators, a grid of tiny rings. They found that this setup naturally solved the matching problem passively.
How does adding more rings make it simpler?
It comes down to having two different time scales. You have light zipping fast around the individual small rings, but the grid also forms a giant super ring where light travels much slower.
So you have a fast lane and a slow lane.
Basically. Having those two timescales meant they didn't need that perfect solar eclipse alignment anymore. The physics of the array provided multiple chances for the light interactions to sync up. It effectively gave them frequency phase matching for free.
That's a game changer. Did it actually work in testing?
It worked beautifully. They tested 6 different chips. They beamed in a standard laser at about 190 terahertz, which is invisible infrared light used in telecommunications. The chips reliably pumped out red, green, and blue light.
Red, green, and blue, the primary colors. And this happened on all the chips?
All of them. And remember, they also tested single-ring devices as a comparison. Even with heaters helping them, the single rings barely worked. The new array worked over a broad range without any active tuning.
So we're looking at a device that is robust, doesn't need extra power for heaters, and can turn standard telecom light into visible colors.
On demand. Right. The authors say this could have huge implications for quote-unquote nonlinear optical computing and metrology. It solves the versatility and reproducibility problem that has held this field back for a long time.
It's amazing how sometimes stepping back and looking at the complex structure, the array, turns out to be the simple solution.
Absolutely. Instead of fighting to control every variable, they found a design that essentially tunes itself.
Well, that is a bright future for photonics. Thank you so much for breaking that down for us.
My pleasure. It's always exciting to see light shed on new discoveries.
See you next time.